Let's take a look at the second free response on the energy test. First, let's scroll through it here, so in case you just want to look at the solution for the parts you need help with, you can do that easily. And we'll scroll back down and then go through it in some detail. But first, you should stop this and take a moment to look over it for yourself. And so we have a pendulum, and it's starting up all the way here. So it's originally horizontal. Let go of it, it swings down here to the bottom. How fast is it going? That is part A. And so the initial energy equals the final. The initial is potential. Final is all kinetic if we say h equals 0 here at the bottom, which is pretty much what everybody did. And so the mass cancels. We get the velocity is square root of 2gh. H was the length of the pendulum, so you get 5.6 meters per second. Second one, how fast is the ball going when it's fallen a distance d? And so it is about here. And so it is fallen distance d, which is given as 0.9 meters. And so you can do it keeping the height 0 at the bottom. The initial equals the final. Start out with potential, end up with kinetic and potential, because I still have some height here. And the mass cancels out again, and you get the square root of 2g times the change in height, hi minus hf. And so the initial height is 1.6. The final height is 0.7. Because if this whole thing is 1.6 and this is 0.9, then this would be 0.7 here. Notice over here I have r equals 0.7. We'll need that later. And so I get 4.2 meters per second. Some people just realize, hey, it's really the velocity is the square root of 2g times the change in height. That's what we have here. And so the change in height, if it's fallen 0.9, is 0.9. So you get 4.2 as well. Part C, what is the total mechanical energy when we are at theta equals 50 degrees as shown in the diagram? And so when the pendulum is here, what's the total mechanical energy, which is the potential plus the kinetic? Well, the whole idea here is that the energy is not changing. And so if I know the energy anywhere, I know the energy any other place in this motion. And so I pick the easiest place right here at the top. The energy is all potential, mgh, and I get 47 joules. Some people went through and figured out how fast it's going here, and they figured out the height, and then they added those two together, and a few of them even did that successfully and got 47 joules, but that took a lot of time. You have to really understand conservation of energy. Once you do that, things get easier. And so there were some partial credit for working out some of that, but very few people who took this approach got 47 joules. There's a lot of places to make errors. If you did get it, you know, that was a pretty good calculation. And finally, determine the speed of the ball when it reaches the highest point in the swing after the string hits the peg. And so if this confused you, you're not paying attention when you're doing your WebAssign, because this is right off the WebAssign. And also Professor Feynman did this in class. And so this swings down, the string hits the peg, and so the ball swings up to here. And so it's got a height of 2r at that point, and r is 0.7, and so the height is 1.4 meters. So depending on how you do it, you're going to need to know that sort of geometry. And so the initial energy equals the final, and the initial is potential. The final is kinetic plus potential, and the initial height is 1.6, and the final height is that 2r distance, 1.4, and I get 1.98 meters per second. Or, those of you picking up on this, it ends up being square root of 2g times the change in height. If we go back here, I'll try and match my drawing. So what is the change in height if it started here and ended up here? And so that's got to be 0.2 meters, which is the same thing you get doing it this way, the 1.6 minus 1.4. So 1.98 meters per second. And then we're asked, the ball is replaced with a ball with a mass that's double the original. It's released from rest in the same position. How will it affect our answer to A? And people did really well on this, but people that had trouble, the reason was they just kind of memorized an equation without going through this process. And so they just had this written here, and that might have got you some points, but you're not really understanding what's going on. And so you don't see what you do over here, that the mass cancels out. If I add more mass, I get more potential, but I also get equally more kinetic. And when you solve for the velocity, it's the same velocity, 5.6. And so I accepted the same because the mass cancels out. Some other people said some other things that were okay, but you have to be careful about what you say here. But there was a point for your explanation. Talk to me if you're not sure why you didn't get that point.